Alright guys, so we're looking at our second part of related rates. This is going to have more application to it than the other ones. So one thing we're going to be looking at is using implicit differentiation. That's where we're taking the derivative with respect to x or with respect to t without solving for y equals in some cases. So we're going to use that implicit differentiation to solve related rates problems. We're going to be looking at circles, spheres, cubes, volumes of cubes, and as well as surface area of cubes. For the first one though, this is just getting the hang of when do we know if dy dt is positive or negative. If we are moving upward, that means dy dt is positive. If we're moving downward, that means that dy dt is negative. For dx dt, if we're moving to the right, it's positive. If we're moving to the left, dx dt is negative. It's just kind of common sense. So this is saying to graph the function y equals cotangent x. Do you remember where the asymptotes are for cotangent? Right? Negative pi, 0, pi, and it says we're only looking at it over 0 to pi. Does this function go up or down? Down. Here's the way it looks. So it's saying over this interval, determine whether dy dt is positive or negative, given that dx dt is positive. If dx dt is positive, that means I'm moving to the right. If I'm moving to the right, what's happening to y? Is it going up or down? Down. So that would mean dy dt is negative when dx dt is positive. All right, looking at the next one. Graph the function y equals tangent x over the interval from negative pi over 2 to pi over 2. Well, that happens to be where the asymptotes are for tangent. Negative pi over 2, pi over 2. When we graph tangent, is it going up or down? Up. It does the opposite of cotangent, so it's going up. Determine whether dx dt is positive or negative, given that dy dt is positive. Well, if I want dy dt to be positive, I have to be going upward. When I'm going upward, is dx dt going to the right or to the left? To the right. So when dy dt is positive, dx dt is positive. All right? Makes sense? Okay, let's go down to some application problems. It says the radius of a circle is decreasing at a rate of 3 inches per minute. We want to think about what that's telling us. The radius is decreasing at a rate. The rate of change of the radius with respect to time, they're telling us is 3. So they're telling us that dr dt, in fact it's not 3 though. When it uses the word decreasing, it's actually negative 3. So I like to jot that down. We know dr dt is negative 3. Find the rate of change of the area with respect to time when, first of all, r is 4 inches and then when r is 2 feet. What's the formula for the area of a circle? Pi r squared. If you don't know these formulas, they are on the green sheet. Now we have to take the derivative of this with respect to time. What's the derivative of a with respect to time? 1, it's just like a y. It would be 1 and then what? dA dt. It's 1 dA dt. When I'm taking the derivative of pi r squared, r is the variable, pi is a coefficient, 2 is the exponent. It's kx to the n. So I have to do k times n, x to the n minus 1. What's that derivative going to be then? 2 pi r. And then what do I have to put though? dr dt. So here's the way we always do these kind of problems. They're called related rates. We write the formula, we take the derivative, and then we substitute. All right, so what I'm trying to find then is the rate of change of the area. This is what I'm trying to find. So I have to know everything else to be able to solve for dA dt. Well, they tell me that the r is 4, and they told us that dr dt is -3. So then just multiplying that, 2 times 4 is 8 times -3. That's going to be -24 pi. Now, we're measuring the rate of change of the area. What kind of units do we use on area? In this case, we're using inches squared, right? Inches squared per minute. So that would be our answer for dA dt. I'm not going to make this lengthy, but if it tells us that r is 2 feet, we can't use 2 feet because whatever this rate is in, this is in inches, this must be in inches. So what would we plug in for here? Not 2, but 24 inches. So I'll just do this one. So we're going to have dA dt then is going to equal, going back to our formula, 2 pi times 24 times -3. This is 6, so 24 times 6, that's going to be 150 minus 8, is that 142, 144? What is that? 144. So it's going to be -144 pi, and then inches squared per minute. Okay? So we don't have to do any, when they do this part B, all we're doing is we're just changing that radius right there to a different number. All right, go over to the back. Okay, so this one says the volume of a spherical balloon is increasing at a rate of 3 cubic meters per second. Find the rate of change of the radius with respect to time when, first of all, the radius is 2 inches, and then it's half a foot. Look at this unit here, guys. This is in cubic inches per second, so this is already in inches, but what would I have to write this as? 6 inches. We're not even going to do that part B. I just want to point out to make sure those units match. So we need to look at our green sheet. If you don't know the formula for the volume of a sphere, do you know it or not? So on your green sheet down here, if you don't know it, volume of a sphere is 4/3 pi r cubed. So we're going to do 4/3 pi r cubed. We're taking the derivative with respect to time. So what's the derivative of volume with respect to time? dV dt. This is a constant, this is a constant. These are both coefficients. Here's my exponent. So I have to do my coefficient times my exponent. What's 4/3 pi times 3? So we're going to have 4 pi r to the second dr dt. It's the same process. Formula, derivative, substitute. Okay, now look at what it says. The volume is increasing at a rate of 3 cubic inches per second. So that's telling us what then? dV dt is 3. And because it's increasing, it was positive. Notice on the other one, they use the word decreasing. So when it says decreasing, it's a negative. All right, so we've got this. We're plugging in 3 for dV dt. Radius is 2. 2 squared is 4. dr dt. We're trying to solve for dr dt. We have 3 equals 16 pi dr dt. Divide by 16 pi. And so dr dt is going to be 3/16 pi, and this would be in inches per second. That's the exact answer. That's a good answer. Sometimes, though, we need a decimal approximation. Here's how I see people type this in, which is incorrect. 3 divided by 16 pi. That is not the correct answer. What our calculator does is it's doing 3 divided by 16, and then it's multiplying that answer by pi. You have to type it in like this. 3 divided by parentheses 16 pi. If you don't use the parentheses, it's going to be wrong. Be careful on that. So it's 0.05, 0.06, I guess we'll call that. So this is approximately 0.06 inches per second. So very small amount that it's changing. Okay, like I said, we'll not do part B, just realize you put in 6 inches. Okay, number 5. A cube has edges that are decreasing at a rate of 2 centimeters per second. How fast is the volume changing when each edge is 3 centimeters? We need the volume of a cube. The room we're in is close to being a cube. Anytime you want to know the volume of something, it's area of the base times the height, as long as the bases are the same size. So for this room, it's area of the base times the height. Assuming all these edges are the same, what's the area of the floor if they're all the same size? X squared for just the floor, right? X times X, then times the height, which is also the same. X squared times X is X to the third, right? So our formula then for the volume of a cube is V equals X cubed. We have our formula, so first we do the formula, now we do the derivative. What's the derivative of V? dV dt. What's the derivative of X cubed?
Please excuse the interruption, but at this time, Mrs. Weber's English classes can come on down. The buses have arrived.
dx dt.
Mrs. Weber's English classes can come on
So
down
now
to get on the buses.
we're going to have to substitute everything in. So we've got the edges of the cube are decreasing at a rate of 2 centimeters per second. So we're going to have to plug in -2 for dx dt. We're going to plug in 3 for x, so 3 squared is 9. And then we have this 3. And so now simplifying this, we're going to have 3 times 9, that's 27, times 2 is going to be dV dt is equal to -54. Think about what units we use for volume. What kind of units? Well, centimeters cubed though, and then it's per second. And that would be our answer. Part B, even on your homework, guys, you don't have to do the part B's because all they do is they just change the number. But what would you do if you had to do 1 meter? Not put in 1 meter, but put in what? But what's 1 meter in centimeters? 100. 100 centimeters in a meter. Where'd you get 72?
I don't know.
It's very random. I don't know anything that's 72. I don't know. All right. Last one. How fast is the length of each edge of a cube changing when the surface area of a cube is changing at a rate of 36 square centimeters per second and the length of each edge is 3 centimeters? All right, so now we're talking surface area. Surface area would be if we were going to take this entire room, we're assuming it's a cube, and we were going to cover it in wallpaper. The floor, the ceiling, everything. What's the area of the floor? X squared. What's the wall? X squared. How many of those X squareds are we going to have? 6. So to find the surface area of a cube, it's 6x squared. You can use your brain to figure that out, or you can use your handy dandy green sheet to figure that out. Surface area of a cube, S equals 6sx squared. All right, so taking the derivative, what's the derivative of S? ds dt, right? What's our derivative here? Good. Everybody got that? If you want, this green sheet is to help you. You can write anything you want on it. If you want to put this derivative on there, you can put it on there. If you feel like you don't know how to find it, but you should be able to find it pretty easily. Okay, so now we're going to substitute in what we need to. So looking at this, we're going to substitute in, we want to find how fast the edge is changing. So we're trying to find this. The surface area is changing at a rate of 36 square centimeters, so 36 for the STT. And they tell us that each edge is 3, so we're going to plug in 3 for x. So then we're going to have 36 equals 36 dx dt. Divide by 36, dx dt equals 1, and that's going to be centimeters per second. Yes. You got to look back at your units. Okay? So it's not difficult. Every time it's the same thing. Find the formula, find the derivative with respect to time, and then substitute. Any questions? All right, your assignment's on the board. Page 149, 9, 10, 15, 16, 18 through 21. If there are A, B, C parts, you can just do A.